Hi, my name is Tatsu Monkman, and today we'll be giving a lecture on how to use calculus to analyze the physical phenomena of centripetal motion. Centripetal motion, the simple movement of an object in a circular path, is conceptually very simple, but is of utmost importance to our physical world. Centripetal motion allows us to build roller coasters, keeps our cars from flying off turns, and maintains the shape of our galaxy. But as I said, centripetal motion is very simple. We can easily describe the centripetal motion of an object using two orthogonal vectors, a velocity vector and an acceleration vector. To keep things simple, we will consider two vectors that maintain our circular motion, instead of flying off in confusing spirals, such as this case where the velocity is too great for the acceleration to maintain. This seems like a very basic form of motion, but this begs a question: how do we model this mathematically? Let's start out in a Cartesian coordinate system, where the path of our object can be described by relating the radius of our path to the x and y coordinates of a given point on the path, and the angle formed by the displacement vector. Notice that our equation looks very similar to the equation of a circle. We can immediately notice a couple of things about our equation: that it moves only in a circle, which makes things easy, that the radius does not change, and that the angular velocity is constant. We can easily graph this in an x and y coordinate plane as shown. This is a good start, but if we want to find out more about our object's motion, we're going to have to start using some calculus. First, let's redefine our theta variable to allow us to take the derivative of our function with respect to time. As we know, w is simply equal to the angular velocity times time. Taking the derivative and the double derivative of our new function gives us the tangential velocity and centripetal acceleration. This derivative is relatively easy to take with respect to t, as long as we kind of ignore the x and y hat coordinate direction vectors. Substituting our r equation back in allows us to solve for our acceleration simply in terms of angular velocity and our radius of motion. We can also accomplish this derivation through the use of vectors. We already know what our velocity and acceleration vectors look like, but what about our angular velocity? Well, we know that our angular velocity is equal to the derivative of theta with respect to t. Using the right-hand rule, we know that, therefore, our angular velocity vector is pointing straight up. This is interesting, because therefore our tangential velocity, angular acceleration, and our displacement vectors are all orthogonal, and hence we can write our velocity vector in terms of the cross product of our angular velocity and our displacement. Therefore, our cross product is equal to the derivative of our object's position, which can be rewritten using the definition of the derivative. So let's simplify this to get a clean expression for acceleration. We know that our velocity is simply the cross product of our angular velocity and our displacement vector, so we can simply take the derivative of our velocity with respect to t to find our acceleration. This gives us an ugly and confusing cross product chain that we can luckily solve using something called the Lagrange formula. The Lagrange formula states that the cross product of a vector A with another cross product of B by C is simply the difference between B times the dot product of A and C times the dot product of A and B. Using this, we find that the expression for our acceleration is simply equal to the angular velocity times r squared. This looks pretty familiar, but we're not quite done yet. With one more simple step, we find that our acceleration has a magnitude equal to r times our rate of change theta, which, again, is simply equal to r squared times theta, QED.